All right, today we're going to pull back the curtain on a classic sorting algorithm called insertion sort. Now, I know that sounds a little technical, but trust me on this one. If you've ever organized a hand of playing cards, you already know the secret. So let's just start with a super simple question. Have you ever been dealt, a messy hand of cards and just instinctively started arranging them, putting them in order by number or by suit? Well, if the answer is yes, then congratulations. You've basically already used insertion sort. Seriously. That little mental process, where you pick up a card and slide it into its correct spot in your hand, that is exactly what this algorithm does. And that's what we're going to break down right now. Okay, so let's make that whole idea a little more formal. First up, Section 1, sorting like playing cards. I mean, really think about how you do it, right? You look at your first card. Well, that's your sorted hand right there, even though it's just one card. Then you pick up the next one from the deck. You glance at it. Does it go before or after the first one? Easy. Then you grab the third card, and you kind of scan the two cards you're already holding from right to left to find its perfect spot. See what's happening? You're building up this sorted hand one single card at a time. Okay, let's take that card analogy and translate it into the core principle of the algorithm itself, which brings us to Section 2, building the sorted portion. So in computer science speak, that sorted hand of cards we were talking about, that's what we call a sorted subarray. And honestly, the entire strategy of insertion sort is just to grow this sorted section. We just keep adding one element at a time, moving from left to right until the whole thing is in order. The best way to think about this is to picture the list being split in two. Just imagine this invisible wall. On the left, you have your nice, neat, sorted pile, and on the right, you have the jumbled, unsorted stuff. The whole game is just to take the very next item from the unsorted side and find its proper home over on the sorted side. That's it. All right, that's enough theory. The best way to really get this is to just see it happen. So let's dive into Section 3 and watch the algorithm in action. So for our example, let's sort this array right here, 5, 2, 4, 8, and 1. We're going to take this thing from start to finish, step by step. Okay, so we always start at the very beginning. We look at that first number, 5, and we just consider it our sorted subarray. I mean, it's only one item, so by definition it's sorted, right? Everything else, the 2, 4, 8, and 1, is on the unsorted side of that imaginary wall we talked about. Okay, step 2, we're going to pick the next element from the unsorted side. In this case, it's the number 2. Now our whole job is to figure out where this 2 belongs in the sorted part. And how do we do that? We compare it backwards. So, is 2 less than 5? Yep, it absolutely is. And since 5 is the only number in our sorted section, well, that was easy. We've already found its spot. So, we just shift the 5 over one spot and pop the 2 right there at the beginning. And look at that. Our sorted subarray has officially grown. It's now 2 and 5. The rest of the list is still waiting its turn. All right, you know the drill. Next up from the unsorted pile, the number 4. We're just going to repeat the same exact process. We compare it backwards. First, is 4 less than 5? Yes, it is. So we know it has to move. We keep going left. Is 4 less than 2? No. And boom, that's our signal to stop. We just found its home. So we slot that 4 right in between the 2 and the 5. And just like that, our sorted section is now 2, 4, 5. We're making some really nice progress here. Okay, next up is 8. Now, this one's interesting. We compare it to the last element of our sorted part, which is 5. Is 8 less than 5? Nope, not at all. So we don't have to do anything. It's already in the correct place, which means our sorted section just grows to include the 8. Super simple. And finally, our last number, the number 1. Okay, this little guy is going to have to do some serious traveling to find its home. So we pick up the 1, and here we go. Is it less than 8? Yep. Less than 5? You bet. Less than 4? Still yes. Less than 2? Yes again. It gets compared all the way back to the start until it lands in its rightful place at the very beginning. And with that one final move, our imaginary wall has reached the end of the line. The unsorted section is now totally empty, which means the whole array is perfectly sorted. 1, 2, 4, 5, and 8. Done. So that's how it works. But the big question is, how well does it work? Let's get into Section 4 and talk about performance and the main takeaways. Okay, now you're going to see a key phrase on this slide, quadratic time complexity. I know, that sounds super intimidating, but here's all it really means. As your list of things to sort gets bigger, the time it takes to sort them gets bigger. Way, way faster. It's not a straight line. Think of it like this. If you double the number of items, it doesn't just take twice as long. Nope. It could take 4 times as long. Double the list again, and it might take 16 times as long. You can see how for really big, messy lists, that slowdown becomes a massive problem. So let's just boil this all down, okay? Here are the key takeaways. On the plus side, insertion sort is really simple to understand and super easy to implement. And it's actually very fast for small lists or for lists that are already almost sorted to begin with. But, and this is a big but, on the other side, that quadratic complexity thing we just talked about, it makes it a pretty terrible choice for sorting huge, totally random lists. It's really that classic trade-off, simplicity versus raw, heavy-duty performance. And all of this kind of leaves us with a bigger, more philosophical question, doesn't it? We've seen that insertion sort is intuitive, it's elegant, but it's definitely not always the fastest tool in the shed. So it really makes you wonder, in a world that's filled with these super complex problems and even more complex solutions, when is the simplest answer actually the best one?